presenting on the topic of my research, disordered transport in unipolar aluminum gallium nitride, or AlGaN. First, I'd like to thank these sponsors and my institutions for making this research possible. So nitride materials have had a huge surge of interest over the last 2 decades. Despite the progress we have made in this area, we've yet to fully understand every aspect, particularly that of vertical transport within heterostructures in nitrides. Much of the transport studies were conducted using LEDs as test vehicles. We decided to employ a different approach and to use unipolar structures with only one type of carrier as test vehicles instead. This allows us to simplify the study by removing recombination from the analysis. And the question we ultimately endeavor to answer is this: what is the main transport mechanism through nitride alloys? Is it thermal escape, tunneling? Is it percolation through disorder? So far, it's pretty difficult to answer. One such attempt to answer that was a study conducted back in 2017 by David Brown and Mika Fireman at UC Santa Barbara, where they studied unipolar electron transport structure of AlGaN, as shown in this diagram here. Due to the polarization and band offset, simulations predict that AlGaN would present a barrier to electron transport. Over here is a 3D calculation I made from the software, with the DDC software developed by Yuren Wu. However, the experiments showed that the AlGaN does not actually produce a barrier, acting more like an ohmic junction than a diode with rectifying behavior predicted by theory. If you look at the curve here and the green curve here, you can see it does not have any rectifying behavior. It's basically a short. This is independent of growth technique, growth orientation, or dislocation density. This was theorized to be due to the percolation through the compositional fluctuation, which was proven by growing the same structure, but instead of using ternary AlGaN, you would grow a digital AlGaN barrier, which is consisting of superlattice structures of aluminum nitride and gallium nitride with the same average composition. And what they found was that the rectifying behavior is restored when you use digital AlGaN because of the absence of these percolative pathways. These proves that percolative pathways are the dominant mechanism for electron transport in AlGaN. So my study was to instead focus on holes instead, using the same type of p-type unipolar heterostructures. To start, I conducted 1D and 3D simulations of this structure using the same software I mentioned. This software uses the Gummel algorithm, which solves Poisson and drift diffusion self-consistently, using the landscape equation as a way to accelerate the computation in a 3D mesh. Once the values converge, it outputs the converged profiles here in 3D and obtained from the full calculation. I used the software to simulate the IV and band diagrams for this structure here, which is consisting of 2 magnesium dope layers, sandwiching a barrier layer of different types. The figure on the left here is the full band diagram of each of these barrier types. And here is the zoomed in version of the valence band. As you can see, the different barriers, different layers correspond to different barrier types, with the 40 nanometer undoped AlGaN presenting the largest barrier to hole transport. By doping the barrier, as you can see here, the barrier is reduced. This is how the hole would flow in the structure. So in the forward bias, it will flow from left to right, and in reverse bias, it will from right to left. This shows that the holes see a different barrier going from left to right and right to left. And then I plotted the current voltage behavior from the simulations. And it was found that the undoped AlGaN produces a barrier to hole transport, as shown by how long it takes to turn on the voltage, turn on the diode. So this rectifying behavior is more apparent in the reverse direction rather than the forward direction because of the asymmetric barrier of the valence band. This barrier is removed once you dope the AlGaN, as you can see. The 13 nanometer p-AlGaN barrier becomes a short. Another thing to note is that when you compare the 1D and 3D simulations, the barrier is also reduced, so the added voltage reduces. This is probably because of the percolative pathways that you account for in the 3D simulations. We attempt to replicate the study experimentally, but there are a few challenges. For one, PGAN is really resistive, so it's a higher spreading resistance. So the current will instead would go up the sidewalls as opposed to going through the barrier. So electrical measurements conducted will not be an accurate reflection of the transport behavior of this structure. Also, damaged PGAN due to diode etching would cause a large P contact resistance, which would be unideal. So the solution would be to incorporate a tunnel junction. So because AlGaN has a lower spreading resistance, you would ensure that all the current would flow across the structure. And then this would essentially ensure that all the current flowing through the structure would be flowing through the barrier. However, the solution has a cost, and the cost is a voltage penalty due to the introduction of the tunnel junction, which introduces a barrier to the structure. So the goal would be to optimize the tunnel junction and reduce the voltage drop in the junction. So to that end, we decided to conduct two sets of experiments to optimize the tunnel junction. The first is a doping series where we varied the doping of the tunnel junction on the P and N region. A second series is a ex situ treatment series where we would treat the interface here with different chemicals to see if we can reduce the voltage penalty of the tunnel junction. Test structures were grown via molecular beam epitaxy. They were fabricated in nanofabrication facility via photolithography techniques, and the IV results were measured using a 2-point probe setup. These results are from the experiment. These are the results from the experiment, and the key takeaway is that the higher the doping, the lower the voltage penalty. Secondly, it was found that by treating the interface in the tunnel junction with buffered hydrofluoric acid, or BHF, you would also reduce the voltage drop in the tunnel junction. We then use that the best tunnel junction device, and then use that as a base for our barrier layer. And then we would grow this structure and then study the different barrier thicknesses and barrier types of the structure. And we plotted the IV characteristics on the same plot. Discounting the voltage dropped in the tunnel junction, the experimental trends actually match theoretical predictions. The undoped AlGaN produces an asymmetric barrier, as shown here. There's a higher voltage penalty in the reverse rather than the forward bias. Secondly, this barrier is also removed when you dope the structure. So the gray curve underneath here is basically the structure without any barrier. So it's just a PGAN. So that would be our baseline. And then this voltage is increased as you increase the thickness of the barrier, and is removed once you dope the barrier. The asymmetric nature of the barrier, the asymmetric nature of the voltage is because of the asymmetric barrier in the valence band, as shown here. To make a better comparison, we added the experimental reference current voltage values. So we added the tunnel junction experimental values to our simulation, full 3D simulation values, and to account for both the tunnel junction voltage penalty as well as the series resistance from the contacts. And it was found that despite adding that, there is still a underprediction of the voltage with regards to when comparing simulation experiments. So there are still some gaps in the implementation. To summarize, we've conducted vertical transports. We've made vertical transport structures for both holes and electrons for AlGaN. In the case of electrons, we predicted rectifying behavior from the simulations, but experiments instead see an ohmic behavior. Secondly, for holes, although the trends are matching, it still underpredicts the barrier caused by the AlGaN. And so there are missing physics from our implementation of the 3D drift diffusion analysis of the structure. And hopefully we are able to fill in those gaps in the coming years. Going forward, we'd like to introduce, instead of an AlGaN structure, we would like to study InGaN. So we would introduce a InGaN quantum well barrier to see if InGaN is a barrier to hole transport. We'd also like to improve the tunnel junction performance using InGaN alloys, exploiting both the smaller bandgap of InGaN as well as the percolative pathways to facilitate tunneling through this tunnel junction. We would also like to implement landscape theory in alloy scattering. So a recent calculation done by Coltrane using this formula here, which is the standard formula for calculating alloy scattering in semiconductors. And it was found that his values resulted in a much lower total mobility compared to experimental values. In fact, there are only 1/6 of the experimental values in the Rajan paper here. So hopefully we'll be able to improve this this formula by incorporating landscape theory into the scattering potential, which we think is a good candidate for the scattering potential. And we would like to use landscape theory and the full 3D analysis to design V-defect and whole waveguides for lateral hole injection into the quantum wells, as well as study AlGaN alloys for inter-sum-back structures. That's it. Thank you.
Thank you for keeping in time, and we have time for a couple questions. Nothing. Everybody. One has a question. Yes.
When you look at the barriers for electrons or holes, you see that one is goes one way and the other one the other way. Could you show the slide maybe?
Okay. Oh, sorry. Talking about this one. Sorry.
Don't go
this one.
Yes. No. Just the next one. I think. The one before. The one before. Yes.
Oh, the one before. Oh, this one. Okay. Yeah, this one.
So could it be the fact that the band offsets are not correct and that you have a smaller band offset in the conduction band and a larger one in the valence band? It sounds absurd, but it would correct in the good direction for both of them at once.
The band offset I use is 6040, which is the standard band offset most simulations used. I haven't looked at changing the band offset in my simulations. I could try that, but 6040 seems.
Is it so? Well, 6040 I know is the one for InGaN GaN. Is it so well known for AlGaN GaN?
Good question. I guess.
But there should be a fair number. There should be a fair number of measurements. You know, we should look at the internal photo emission literature.
Yeah.
IPE. And you can also look at Christoph Ernie measured the band offsets using Kromer's CV method. And I think he, you know.
He was not so sure what he measured actually.
But I would look at the internal photo emission.
Okay.
We should look at the IPE.
Okay.
But actually, go back one slide, please, Clayton. I mean, we had, this was work on the right panel, right half. We had known this with UREN, but sort of this was done, the full implementation of 3D DDCC with UREN sort of happened near the end of Mika's time and after David Brown was left. So this is a combination of Mika experiments and David experiments, but we still struggle to explain even the unipolar transport in AlGaN. Well, I don't know if it's because we don't have hopping. We need to, I was chatting with Clayton, we need to do more temperature dependent measurements. I don't know how much Mika did, I can't remember. And we have no tunneling, but the right slide is a big deal because we're failing with AlGaN. I mean, and probably we would also fail in the unipolar transport for InGaN.
Jim, this is a self-consistent computation, but it relies quite a bit on, you could have charging effects. You could have, I'm not sure you would be always in equilibrium as you assume when you do the self-consistent computation. And then if you have charging effects, everything can happen.
I don't think there's, I mean, I don't think you're having, no, I don't agree. I don't think they're charging effects. You would see, I mean, we can measure that in frequency dependence. I don't think there are any charging effects. These things look like ohmic shorts. I don't agree at all.
You could have a transient.
Yeah, we would see it in frequency dependence, which we should look at.
I agree.
But I would bet strongly that that's not the case, particularly for the N-type behavior. So I think, you know, for Abel and Marcel, and if Irene is probably not awake right now, but he was on earlier, you know, we need to think about it. Is this tunneling? Is this hopping? We have to do some more experiments. So we're going to go back and try to recover these samples and do temperature dependence. We can look at frequency dependence, but it's a huge shortcoming of our implementation. The reason we looked at unipolar structures is that nothing is hidden in recombination coefficients. And that's my worry. When we model LEDs, we have everything we can hide all the shortcomings in recombination coefficients. And here there's no hiding. This is bare and exposed. So Claude, as critical as we are of DFT, we should look at our own data and be very critical here.
No, it's not the same. Wait, it's not the same physics as in
Claude. I think that we're gonna have time for discussion after, but for interest of schedule, we should keep on and we should move. We should thank Jim and thank the speaker.
Clayton.
Thank you.